Hi, Professor. This is Srinivas Teja. Previously, my teammates Ajay and Siva explained how the slicing is done and how we assign values to the robust variable. And in this slide, I am explaining the size of the slices produced. For the example program used in the case study, a robustness slice construction algorithm should be able to produce the ideal robustness slice, that is the simplest possible slice, which is the final step below. That is, we will see the final step, revealing immediately that the original program is not robust. Providing transformation rules which would produce such a slice is less difficult than it seems. In order to move from step 4 to the final step, previously we've seen the step 4 and now we'll see the final step. All that is required is a transformation rule which exploits the fact that the Boolean expression of a while loop is true at the outset of the execution of its body, and that the result of the Boolean operation, which is a logical operand, is false whenever either operand is false. Of course, due to the fact that robustness is undecidable, because the robustness will change based on the variables, it will not always be possible to produce an ideal slice. Such as this example, we take the final step where the robust is equal to 0. And we use some more complex language semantics where the language small c is extremely simple. When we consider a language small c, which is a subset of C programming language suitable for resource limited microcomputers and embedded systems, and an implementation of that subset. Originally, the small c program is used for microcomputer systems, which is available for 70s and 80s. And this also useful for as an example, simple enough for teaching purposes. Whereas this small c was introduced by Ron Kane, which is in May 1980. And it is a retrogatable compiler. Porting small c requires only that the backend code generator and the library to operating system interface calls be written for the target processor. In this, we see some, although this is commonplace today, it is a very novel ideal at that time. His compiler generated assembly language for the 8080 processor. And sorry, Professor, previously I missed one slide, which is the table given in figure 6 gives the sizes of each program produced in the course of the case study, where size is the number of nodes in the program control flow graph. It is of the nature of the approach that the size of a program will increase as the result of side effect removal and the introduction of the pseudo variable robust. The hope is that in many cases, the simplification produced by slicing and transformation will yield a robustness slice, which is significantly shorter than the subject program. This will be an objective measure of simplification that can be used to assess the suitability of the approach on a case-by-case basis. We consider here the case-by-case basis, and the robustness slice, which will always be semantically very simple. We have seen so many in the previous slides, as it is merely concerned with storing one of the two values in a single variable. This alone may make the robustness slice easier to analyze than the subject program. The principal task for further work rests upon speeding the best transformation tactics with which to simplify the slice produced. Here we just simplify the slice because we get difficulties in that while preparing. It is upon the power of the slicing and simplification transformations that the applicability of the robustness slice approach critically depends. And previously I told you, like, the small c language is extremely simple, and the simplicity hides some issues which arise when a large subset of c is chosen. It is the small c is used only for minor codes, but not for the bigger ones. For example, when arrays may occur as the parameter to a function, The function definition need not specify the array bounds. Each call to the function can potentially pass an array of different length. Each call to the function can potentially pass an array of different length. We use different lengths in order to correctly assign to the pseudo variable robust. An extra parameter to such function definitions will be required, giving the length of the array parameter. Here we just assign some length to the array parameters. And however, this extra parameter may be introduced merely by defining another class in the definition of TA. Similarly, issues arise with the dynamically allocated storage and with the exploitation of the array pointer duality in C. And some related work we done for this is the Rosenblum has implemented in 1995 a preprocessor system called APP, which replaces the traditional C processor, because in the traditional C processor we cannot do the bigger codes, so we implemented this preprocessor called APP. In addition to the normal C preprocessor tasks, the APP recognizes comments of the form as containing assertions about the state of the program. An assertion takes the form of pre and post conditions at the functional level of abstraction. The preconditions capture the set of initial states in which the programmer expects a function's body to be executed. The post conditions capture the set of final states in which the function will terminate. So here the function will terminate in the final states. The two different post conditions are permitted, which is a promise of E, which delimits the set of admissible final states for the function body, and return I where E, which constrains the possible values returned by the function. And the assertions recognized by APP are introduced by the programmer and are checked at runtime by code added at source level by the APP preprocessor. We completely use now APP preprocessor to check the runtime and everything. The robustness slice approach, by contrast, does not require the programmer to add the assignment statements which capture the program's robustness. Rather, these are added automatically by the transformation function T. The programmer is then expected to analyze the robustness slice produced by slicing and information. David Flatter and his colleagues describe an extension of the C programming language in which assertions concerning inter alia robustness are automatically added to the C program to create a program which performs checks upon its behavior at runtime. The process of introducing checking code for the integrity of array indexing is almost identical to the process of adding assignments to the pseudo variable robust. The principal difference between robust C and the robustness slice approach is to be found in the way the self-checking program is used. Here we use some self-checking program to just check the robustness of the slice, and the robust C program is executed with invalid array indexes, causing the execution of the program to terminate with an appropriate error message. We terminate the program when we get an appropriate error message. Now my friend Vishwanath will explain the remaining part.